if you'll be able to use MATLAB and you can practice using it to add more poles. And here we only add one pole for example here. Okay. Here using the same example here, and let me case 3. So this one I think we compare to our original and this is case 2 adding. So case 3 is 1 plus k as plus a, and here we have the 0 here, so that is s plus b. Equal to 0. So here is b plus a equal to 0. So here we have both 0 and minus a, we have 0, and that is minus b. Again, we can do this one. We can add zeros by modulating the content of controllers. Usually, in many systems, we have our controllers are implemented in circuit board. So which means, and that will be additional information you might on one side work with the electrical engineers. They have the certain classes, the 300 level, I think by the next quarter, taking this one, the microcontroller design. On the other side, you can go to take classes directly by yourself. And the controller design, basically, in terms of circuit, they basically integrating the different, the schematic of the feedback loop. And that one, they usually modulate, you'll be able to modulate resistors, conductors, and capacitors all combined, and to achieve this thing. And of course, the circuit board, usually they come with is a very tiny signal and microamps and millivolts. And usually they will come up with, if you want to use circuit board to drive, for example, the motor, which is our mechanical system, you have to combine with the op-amp, operating amplifier, and even the power electronics. So most of the time when the people say in our school here, we have a control class in mechanical engineering. And in electrical engineering, they also have their control class. We talk about the same concept, but when we implement this work, there are different philosophies. But most of the time, in both fields, you have to work together. Okay. So we add a 0 here. So here we can see what happens. So here is our root locus and real part and imaginary part. So we have 0 and here and here. Okay. So here is s equal to 0 and k equal to 0 and s equal to minus a, k equal to 0. And here is s equal to minus b and k approaching to infinity. So we have this one. Then again, we try to make the root loci. That is again on the real axis to the left of the odd numbers of the point 0. The other one here. Okay, goes to infinity. And the directions will be like this. We're starting from here and starting from here. So increasing, when we increase the value of k, the branches will be here, and they will be somewhere, and we will determine the breakaway point. So here is a breakaway point. Okay, so here is the breakaway point. We can determine again for this one is dk, ds. K will be equal to 0. So here for this case, we can calculate K will be equal to s squared plus as s plus d. Okay, so that means we have to require 0 equal to d ds.
Is that negative?
Yes, thank you. Okay, but here they may drop the negative. Yeah. Okay. So you implement this one. how much, whatever. So here we pretty much sure the breakaway will be somewhere in between. Okay. So allow me to skip out this one. To solve for this one, then you will know the position. So the breakaway will be here, somewhere here. Okay. And for this one, we how to continue. So here we know the things will be again when k is increasing, the will converge to the 0 here. So so since we have to solve for this one, and here we should have the two values. Let me solve for this one quickly. For this one, qs plus a s plus b minus s squared plus s plus b squared, okay, equal to 0. I take the same rule. So that is qs plus a s plus b minus s squared plus as equal to 0. So here is 2s squared plus a plus 2b s plus ab minus s squared minus s equal to 0. So here s squared plus 2b s plus ab equal to 0. Okay, so here let me solve for this one quickly. 2 minus 2b plus square b squared minus 4ab, right? So that's a 3 minus b squared plus minus ab. Okay.
So do you not care about the denominator?
Huh?
Wait.
Whatever. And yeah, you can double check this number. Any mistake?
Well, I got
I think
I got-
shouldn't you have 2s squared before that?
No.
These are two roots, right?
Wait, never mind.
Okay. So for this one, b is greater than a, so this is a real part. This also is a real number here. So here we have two roots, and one is minus b plus some positive number, and one is minus b minus some positive number. So here, let me just assume one is here and one is here. Okay, so that is one is breakaway in, one is breakaway, one is break in. Okay, if you remember, this equation is to tell us to find the repeated roots for certain value of k, and that is the essence of this equation behind. Okay, so here again, this equation is to calculate the repeated roots of the characteristic equation for certain value of k. And repeated roots, and here we have calculated repeated roots of the real numbers, so here is 1, here is 1. So from here we know that once the branch break away here, then one branch will be coming, go to here, and for this order, lower order system, we pretty much sure that will be the simple curve, okay? And this one go to here, and that one go to here. So this is breakaway. And this point is break in. Okay. So that's the kind of schematic drawing, and from here we pretty much finish all these things. And here we, if you really want to calculate asymptotes, you can determine. But here we don't have other information we can go forward. So we stop here. Okay. So now we have our original system like this, and we add in a 0. You look at, we compare the root loci in this range. Okay. And the conclusion is. Anyone?
More zeros.
Yeah, more. We can see the root loci after adding 0, this branch will be dragged towards this way, right? Towards this region. That means drag the root loci more towards the negative, which means the system will become more stable. More stable. Okay. Yes.
What happens if you add both?
Hmm?
What happens if you add both the 0 and the pole?
Yes. So it could be possible if we have the both 0 and pole together. And very likely is this, if you want to fine-tune the system, for example, in those things usually happen to the higher order system. Higher order system, that means allow you more degree freedom. If you want to make sure, say, for k equal to, say, lower range, say, k equal to 10, you want the system is more unstable. And for k value, say, k equal to 1,000, you want the system to be stable. So that will give you allow the flexibility, and you can see the root loci will be kind of the more distorted. And so that could be, I won't guarantee, but schematically, the root loci could be like this. In this range, the things will be something like this. And then more toward, it will be going like this one. Like kind of, you can play around using the MATLAB. Okay. And
You're not going to give us something like that, though.
for higher order system, it's possible. And in particular, here we talk about in the lower order system, even second degree, and that the second degree polynomial and the degree system, that is always our content of our test homework. The third degree, that is the limit I would dare not to exceed. Otherwise, I will get a backfire from you.
You're right.
Yeah, but if you be pursuing the graduate study in terms of master degrees, then your project will be like this. I can share with you my experience. When I was a graduate student, my project is on the control of the flexible beam. And if you remember in the two questions I will answer later. So this is the beam. Okay, so that's a cantilever beam. And cantilever beam in your ES mechanical material will climb against the wall. But usually this one in reality is attached with a motor. The motor will make the beam to switch in this way. Okay. And if the beam has the very thin cross section, you'll see what happens. Basically, I just similar like hit the old school teacher, they using the ruler to hit it. Like this one. For this kind of system, you can see that is very flexible. If we using motors to start with, and then the end, basically you can tell if without any control, the tip end basically is very free vibrate, take a long time to suppress. So the application of the flexible beam at that time in the end of the 1980s, beginning of the 1990s, that one due to the development of the space shuttle, and they deploy the satellites and also other purposes. Usually they have designed the flexible, they have to make the robot arm. They compose of the 1 or 2 or 3 links of the flexible beam, and they're made up by Canada. They deploy the satellite to the right positions as soon as possible. You can see what happens. Satellites have mass. It's deployed, want to get there as soon as possible, then once you get there, that's a position, then you can see the beam will begin to vibrate and then going there. So the whole thing basically is a conflict of interest. You want to move the heavy things with the light arm to the right position as soon as possible and stay there. Basically, it's conflict of interest. So the way is you have to modulate the controller. If here my joint is a controller, once I get here, then my controller will control the motor here, kind of begin to back and forth, set motor back and forth, to do the active way to counteract with the vibration of the beam. Okay. And in this case, the beam usually is modeled, the beam is a continuous system, which means have an infinite number of the degree have an infinite number of the degrees of vibration, the degree of freedom. And most of the time we using the advanced modeling techniques, and we call the model decomposition. We will be able to decompose the system into the finite number of the degrees of vibration system. And that kind of decomposition is not through the time domain, but in the frequency domain. In the way that will be better approximation. But anyhow, we will be able to approximate the continuous system from the many degree freedom system to say 4, 5, 6, depends on what we desire. Okay, and then we proceed the controller design, and then we play on our approximated systems, and we do the simulations, and then we develop the system to benchmark our simulations. So that's the whole thing. And many times, and the story happened here, we encountered this kind of things. And usually we play around the controllers. We add in something, we reduce something. And sometimes the added port will cancel the zero of the original system. Sometimes we add zeros which will eliminate. For example, if you by chance select B equal to A, you will cancel this one. And that sometimes gives us certain trouble. And we'll talk about this one. This one is called the pole zero cancellation. And this one basically you will kind of drive your system into the certain mode, certain controller mode is become hidden. Become hidden, that means you will never be able to control that particular mode. And if that mode is critical in your goals, then you will have a big trouble because you lose it. Okay, so that is the whole thing. So 2 questions. You
That was
first.
my question. What would happen if B was equal to A?
Yeah, so that's a pole zero cancellation. Basically, or I will talk about that one in 1 minute. So, Tim?
You talk about adjusting K and like going through different values. How do you actually, like, can you give an example of adjusting K?
K, yes. And that will be the next topic, the
Okay.
PID controllers. Okay. So that is my, over this weekend, I'm kind of thinking, after we finish the root locus, which will, Wednesday we'll have our test, and then Friday we kind of have time to go over the test, and then have time to begin another design part using root loci. So root locus, I think will take 1 or 2 more lecture hours, and then we'll finish. Then I calculated we pretty much don't have much time, pretty much 7 lecture hours or up to 8 lecture hours. We have 2 big topics, and I'm kind of the 50-50. I'm still evaluating. One topic is the it's more toward the modern control system than using state variable, and that's a totally new techniques and focus in the time domain. The other big part is continue on the frequency domain, and here we will move towards the in the frequency domain, still continue in the complex function, complex methods approach. And that one will pretty much like your vibrations, the harmonic vibrations. When you do the harmonic vibrations, you simply introduce S equal to Z omega. Or in your harmonic excitation, you simply introduce sine or cosine of the different frequencies. So that is a different story. So I will ask you again maybe Friday, and if you prefer, I don't know which one you prefer. So sorry I talked too much, and someone begin to play games on the cell phone, and someone begin to one thing. For the controller things, and we will get more insight with the modern control system. Okay, but in terms of the frequency domain design, we have more techniques and it's more relevant to what we are learning now. So I will continue thinking. Okay, so now the next one.